All right, good to see you, or have you seen me, or whatever. So this week, hopefully, you had a chance to watch the three videos, short videos on bonding earlier in the week. And I've noticed that a lot of you have turned in your Cornell notes on the reading from pages 602 to 606 in the chapter. Hopefully you've done all those things. If you haven't done all those things, would you press pause on this and go do those things first, because this will make more sense if you've already done those things. All right. So what we're going to talk about is bonding, especially a type of bonding called ionic bonding. And in order to do that, we've got to use the periodic table, or at least some shortened version of it, because this will be enough to do what we need to do. We've got to recall and remember, and we'll do a little review of how to know how many valence electrons there are and what those valence. And then we're going to talk about the octet rule, okay, and how that comes into play with ionic bonding. All right, so let's start out by talking about the periodic table and valence electrons. First of all, again, it's not the whole periodic table, right? It's just the first 18 elements up to argon, okay, with this whole section we're leaving out. Now, that whole section isn't involved in the first 18, but I want to remind you, when you look at your periodic table, what's in this middle section from groups 3 to 12, you're going to learn about that when you're in 11th grade. But right now, it's really strange what happens in there, so we're not going to worry about it. What we are going to talk about it is groups 1, 2, 13, 14, 15, 16, 17, and 18. Because those 8 groups are the ones that behave most predictably when you're talking about valence electrons and bonding. Okay, so let's focus on those. First of all, valence electrons. Remember, valence electrons are in the outermost energy level. They're the ones that are involved in bonding. The electrons in the inner energy levels are not involved in bonding. Another thing to remember, the first energy level, the innermost energy level, only has 2 or room for 2 electrons. Hydrogen has 1, so it doesn't have a full energy level. But helium does. That's why it's in this column. We'll talk more about that later. Helium has 2 electrons, but in an energy level, the first energy level, that only can fit 2. All the rest of the energy levels can fit 8. And that number 8 is important, which is why we're going to get to the octet rule. Okay? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. There's a reason there are 8 elements in that row. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. There's a reason there are 8 elements in that row. 8 is important. The octet rule is important. All of the elements in this column are called noble gases, and they are that because they have complete outer energy levels. For most of them, it's 8. For helium, it's 2 because it's that inner first energy level, right? By the way, that pounding you're hearing, maybe if you're hearing it, there are people working in my basement, so don't worry about it. But this column, most of them have 8, octet rule 8, outer shell valence electrons. Every other column has fewer than 8. How many does it have? How many do each of the columns have? Well, remember, that's pretty easy. There's a pattern, right? This first column, each of those has 1 valence electron. The second column, each has 2. The third column over here, well, the 13th column, but we're taking that middle section out. So really, it's the third column. Each of these have 3, boron and aluminum. 4, 5, 6, 7, 8. So you can just count from left to right and know, or you can use the numbers up above. Row 13, really that's 3 valence electrons. Row 16, oxygen and sulfur, that's 6 valence electrons. So that's the quick and easy way to remember and to find how many valence electrons each of those elements have. It all depends on the column, and every element in the same column has the same number of valence electrons. A very important pattern of the periodic table, not a coincidence. The periodic table is what it is because every element in the same column has the same number of valence electrons. Okay? All right, so valence electrons. Very important that you remember how to find those. Now let's talk about oxidation number. For this, we have to remember octet, 8. Every element wants 8 electrons, a complete outer energy level. It can gain electrons to get 8 when it combines with other atoms, or it can lose electrons to get 8. It can gain electrons to get 8, or it can lose electrons to get 8. Well, Mr. Morgan, how do I know which one it does? Well, typically it does whichever is easier. For instance, in this column, fluorine and chlorine have 7 valence electrons. Do you think it would be easier for them to gain 1 or to give away 7? Well, if you said it seems like it would be easier just to gain 1, you're right. It's much easier if you have 7 to get 1 more than it is to give 7 away. On the other hand, lithium and sodium only have 1 valence electron. Do you think it'd be easier for them to gain 7 or just to give 1 away? And if you said, well, wouldn't it be easier for them to give 1 away than to gain 7, to find 7 random electrons out there to bring them in? Yeah, that would be easier. Give 1 away. So typically the metals, which are on this side, right, the left-hand side, we've spent a lot of time with metals and nonmetals in this unit. The metals tend to give away electrons, and the nonmetals tend to gain electrons. Now, because of that, the metals tend to be positive ions, and the nonmetals tend to be negative. Because if you gain electrons, remember electrons are negative. If you gain electrons, you're going to become more negative. You're going to become a negative ion. But if you lose electrons, you're going to become a positive ion. Because if you give those electrons away, then you've got excess protons left, and that's positive. How positive and how negative? Well, if you give away 1 electron, you're a +1. Beryllium and magnesium have 2 valence electrons, and they can give 2 away to have an octet and be +2. Whereas over here, fluorine and chlorine, they're going to gain 1 and be a -1. Oxygen and sulfur have 6 valence electrons. They need 2. So when they gain 2, they are a -2 ion. This is -3. This is +3. And then you might be like, oh, wait a minute, Mr. Morgan, carbon and silicon and all those, they have 4. It seems like it would be equally easy to gain 4 or to give away 4. And you're right, which is why we say in this column, it can go either way, plus or -4. Depends on what they're combining with. If they're combining with things over here, then carbon and silicon tend to gain electrons because these really want to give them up. But if they're combining with things over here, then carbon and silicon want to give away electrons because these tend to want them more. Okay, so it can go either way in that 4th column. But nonmetals tend to be negative ions. Metals tend to be positive ions. And the octet is the rule. How many electrons do you have to give up or get to get 8? Now, these numbers down here are often referred to as the oxidation numbers. Fluorine and chlorine have an oxidation number of -1. Beryllium and magnesium have an oxidation number of +2. Carbon and silicon are plus or -4, depending, okay? Those numbers are referred to as oxidation numbers, and those numbers are important because they tell us how many of each element you need to bond to make a compound. How many of each element you need to bond to make a compound. And the key is neutral, balance. The positives and negatives have to cancel each other out. And for the simplest example, we'll start with the thing we started the semester with, dihydrogen monoxide, H2O. Water. We're starting with water because it's the thing we're most familiar with, and we talked a lot about it way back in January. Why is it H2O? Why does it take 2 hydrogens to bond with 1 oxygen to make water? And the reason is the oxidation numbers. Hydrogen likes to give up 1 electron. So each hydrogen has an oxidation number of +1. Oxygen, with 6 valence electrons, likes to gain 2 electrons to get to 8. So its oxidation number is -2. So how, when hydrogen and oxygen get together, how do they balance each other? Well, 2 hydrogens, 2 + 1 is a +2, and 1 oxygen. is a -2. So you've got a +1 and a +1. You got two of those, and you got 1 -2, and they balance out to 0. The 2 +1s balance out with the -2. That's why it's H2O, because the oxidation numbers have to balance out to 0. The electrons have to get lost and gained in a way that gives you a neutral compound. -2 and 2 +1s. Now, is that only true for water? No, it's really true for all kinds of things that bond together. I'll give you an example, all right? Na, sodium, and chlorine. Na and chlorine. Let's look at their oxidation numbers. Na is right here. It's in the first column. It has 1 valence electron. It would like to give up that 1 valence electron. It has a +1 oxidation number because it would like to give up its 1 electron. Chlorine, Cl, has a -1 oxidation number because it has 7 valence electrons. It only needs 1 to get its octet of 8. So it has a -1. So when you have sodium +1 and chlorine -1, how many sodiums need to combine with the chlorine to balance out and make NaCl, sodium chloride, table salt? If you think the answer is, well, it seems like one of these and one of these, +1 and -1, balance out to 0, it seems like just one of each. You're right. It is just one of each. The sodium chloride is NaCl. Some scientist somewhere didn't just come up with the wild idea that, oh, let's make it NaCl. It works that way because the electrons, the valence electrons, work that way because the oxidation numbers to get to 8 work that way. All right? I'll give you one more. Okay? What about Mg and F? Look at the object oxidation numbers. For Mg is over here, and F is over here. Look at the oxidation numbers. I want you to press pause in a second and figure out in your head what's going to make those balance. How many Mg's and how many F's? I'll tell you, the name is magnesium fluoride. That doesn't tell you anything about the answer, but it tells you the name is magnesium fluoride. My question to you is, how many Mg's and how many F's in magnesium fluoride? Go ahead and press pause. Come on back when you think you got it. All right, are you ready to see if you got it? Let's look at the oxidation numbers. Mg is in the second column, so it's a +2. Fluorine is in the second to last column. It's got an oxidation number of -1 because it has 7 valence electrons. So fluorine's a -1. So to get these to balance out, 1 Mg needs 2 fluorines to balance, right? +2 needs a -1 and then another -1. So the formula is Mg2. 2 fluorines combined with 1 magnesium. All right? Okay, so hopefully that was a pretty good summary of what you should have been doing this week. Again, if you got to the end of this and you're like, none of that makes any sense, my question is, did you watch those videos from earlier in the week? Did you do the reading and answer the Cornell note stuff? Okay, do all that and then come back and watch this again. On Tuesday, we'll take a look at some more examples of oxidation numbers and ionic bonding and the way they fit together. And we're going to have a quiz next Friday. That'll be our last quiz of the semester. Woohoo! All right, great. Have a great weekend. Take care.